Hey everyone, welcome. Today, we're jumping into a real-world physics problem that you've probably seen 1,000 times, but never really thought about. It looks simple, but trust me, it's packed with some super interesting principles of balance and force. So let's get into it.
So here's our subject for today, this pickup truck. It's just sitting there, parked, loaded up with two heavy crates. It seems perfectly still, right? But don't let that fool you. Underneath it all, there's this incredible tug-of-war forces going on, all working together to keep everything in perfect static balance. And that brings us to the big question, the mystery we're gonna solve today. Just by looking at it, what's your gut feeling? Which tires are bearing more of that weight? Is it the front axle or the rear? Let's become physics detectives for a bit and follow the clues to find out for sure.
Okay, so every good investigation has to start by gathering the facts. So what do we actually know about this truck and its cargo?
First up, the truck itself. Our case file says the empty truck has a mass of 1,400 kilograms. That's our starting point. You know, the base weight the wheels have to deal with before we even think about adding anything else.
And next, we've got the cargo. Those two crates in the back, they each have a mass of 350 kilograms. So that's another pretty significant load we're adding to the mix.
So when you add it all up, the truck plus the two crates, we're looking at a grand total of 2,100 kilograms. That is the total downward pull of gravity that we have to counteract.
Now, this slide, this is where we get our most important clues. See, in physics, it's not just about how much something weighs, it's about where that weight is. These distances you see here, between the wheels, from the wheels to the crates, and to the truck's own center of gravity, these are the absolute keys to solving this whole puzzle. All right, we've gathered our clues. Now it's time to open up our physics toolkit. We're going to use some fundamental laws of balance to crack this thing wide open. The main idea we're going to be using is something called static equilibrium. Sounds kind of fancy, but it's a really straightforward and powerful concept. It just means that for something to be perfectly still, like our truck, all the forces acting on it have to perfectly cancel each other out. No leftover force means no movement. Simple as that. And really, it all comes down to these two simple rules. First, all the upward forces, that's the ground pushing up on the tires, have to exactly equal all the downward forces from gravity. And second, all the forces trying to make the truck rotate clockwise have to be perfectly balanced by all the forces trying to make it rotate counterclockwise. And hey, don't let that word moment throw you off. It's just what physicists call a turning force. The easiest way to picture it is thinking about using a wrench on a bolt. The force you put on the handle times the length of that handle, that creates a moment. That turns the bolt. It's the exact same idea with our truck. All right, let's put these laws into action. We're going to start by figuring out exactly how much force is pushing up on those two rear wheels. So here's why we use a really clever trick. To figure out the force on the back wheels, we're going to pretend the front wheels are a pivot point. Why? Because by calculating all the turning forces around that specific point, the force from the front wheels is at a distance of 0, so it just vanishes from our equation. It's a fantastic little shortcut to simplify the problem. Okay, so we take all the clockwise turning forces, that's the weight of the truck and each crate, multiplied by how far they are from that front pivot point. We know all of that has to be perfectly balanced by the counterclockwise turning force from the rear wheels. And when we run those numbers, it turns out the total upward force from both rear wheels has to be 13,047 newtons. And since that force is split evenly between the two rear tires, we just divide that number by 2, which tells us that each rear tire is pushing up with a force of 6,524 newtons. Boom, we're halfway there. Now that we know what the rear wheels are doing, finding the foot forces is actually the easy part. We just circle back to our first rule of equilibrium. Forces up must equal forces down. We already know the total weight pulling the truck down, and we now know how much force the rear wheels are pushing up. So whatever's left has to be coming from the front wheels. It's really just simple subtraction now. We take the total downward force of the whole setup, subtract the upward force from the rear wheels that we just figured out, and what's left is the force from the two front wheels, 7,554 newtons. And just like before, we chop that in half. And there we have it, the final piece of our puzzle. Each of the front wheels is pushing up with a force of 3,777 newtons. So we found all the forces. Now it's time to put it all together, compare our findings, and deliver the final verdict in the case of the balanced pickup truck. And here it is, the answer to our original question, laid out as clear as day. This bar chart says it all, doesn't it? The rear axle is supporting over 13,000 newtons, while the front is only handling about 7,500. It's not even a close contest.
So yeah, the rear wheels are doing almost 75% more work than the front ones. And the reason why takes us all the way back to those distances we looked at earlier, because the cargo and even the truck's own center of gravity is positioned more towards the back. All that weight has more leverage on the rear axle. It really is all about placement. So, we've completely cracked the case for a truck that's just sitting still, in static equilibrium. But this leaves us with one last, really interesting question to think about. What happens to this whole delicate balance of forces when the truck isn't static anymore? The moment that driver hits the gas and the truck lurches forward, how does that change the entire story? Well, that's a whole other dynamic puzzle for another day.